Continue on talking about kinetics. Hope we get to the end here. So last time we got into a little bit more about kinetics. We talked about specific orders of reactions. And again, really based on the number of reactants we have going on and most common reactions, there's really sort of three types of orders that we commonly deal with, and those as first order, second order, and zero order reactions. And these are the common ones that we come across. Come here. Just now we saw some integrated sort of laws that go with these. We have the natural log of A is equal to the natural log of A naught minus KT, where the half-life is the natural log of 2 over K. For second order, it's 1 over A is equal to 1 over A naught plus a KT, where the half-life, is something like 1 over K times A naught. And zero order, A is equal to A naught minus KT. Half-life there, initial over 2K. Also really important here are the units associated with the rate constant. Again, it will tell you basically the order of the reaction you're dealing with. So for first order, the units of the rate constant are typically 1 over seconds. As we talked about, it doesn't necessarily have to be seconds. It could be some unit of time, but it's really reciprocal time. So again, it could be 1 over minutes, hours, weeks, whatever it may be. For second order, typically speaking, we end up with 1 over molar seconds. And once again here, the unit of time can be any unit you want, but usually seconds, very common. And for zero order, it is the same as the rate, which is molarity over seconds, as should be K actually, sorry. So it's important to know those units for the rate constant, because a lot of problems, they really will not sort of tell you straight up, what is going on in terms of the order, but they may give you those units, and you need to know which one to use. Also a reminder that it's very common you need to use kind of both of these equations together. And very commonly, if you do, you probably will be given the half-life, need to solve for the rate constant, and then use the rate constant in the first one. So usually in that situation, you would probably be trying to figure out the rate constant and then going up into the other equation if you needed to do so. Now, there's also some important graphs that go along with these type of orders. For first order, typically what we look at is the natural log of A versus time. Should yield you a straightish line. Should be a straight line there, where the slope of that line is equal to minus the rate constant. You could also see for first order concentration versus time. Will not give you a linear line, but will give you more of a decreasing line over time. For second order, we also would graph typically 1 over the concentration versus time. Would give you a linear line in the positive direction, where the slope is equal to the rate constant. And then concentration versus time, going to yield you a linear line there, where the slope is equal to minus K. Once again, these are the same graph in terms of what is being graphed, but they do not result in the same type of graph at the end. If it is a linear relationship, when you graph concentration versus time, we are dealing with zero order. If it is not a linear relationship, but the concentration basically decreases with time, like we have over here, it is a first order. So again, you'll sometimes see the same graph used, but only one will give you that linear relationship. We then talked about activation energy and sort of energy diagrams and the idea of sort of temperature. And remember that in terms of a reaction, we have our reactants, we have our products. There is a certain hill that basically has to be climbed, which is the activation energy, which is the minimum amount of energy required for a reaction to take place. The sort of how tall that hill is has a lot to do with how fast or slow a reaction will take place. If you have a really big activation energy, that typically means that you will have probably a slower reaction because there will be a less proportion of molecules that have enough energy to get up and over to the other side. If you end up with a smaller activation energy, then typically speaking, your reaction probably would take place a little bit faster. There would be a greater proportion of molecules that have enough energy to get up and over. That's also where temperature comes into play. Obviously, by increasing the temperature, what you are essentially doing is adding a lot of energy. And what that gives you is a greater proportion of molecules that will be able to get up and over to the other side and really meet that activation energy sort of hill. And that usually, again, would speed up your reaction. And as we talked about, sort of vice versa there, if you kind of lowered the temperature, that would be like removing energy, which means that, again, there will be less of a proportion of molecules that really will have enough energy to get up and over that hill to the other side. The ultimate result of that is you probably would see a slow down in your reaction rate or slowing of your reaction rate. Remember that the difference between the reactants and the products, right, is the delta H of the reaction, right, the enthalpy. There is a relationship, which is the Arrhenius equation, which we saw at the very end there, which is the natural log of K is equal to minus E of A over R, 1 over the temperature. Plus the natural log of A, I think. So this is Y is equal to mx plus b. So a typical graph there would be our natural log of K on the Y, or 1 over T, and this will yield us a straight line where the slope is equal to minus E of A over R. So graphically here, this is how you can graph and figure out the activation energy for a reaction if you have the rate constant and obviously the temperature as well. All right, any questions on that there? All right. So I think this is sort of right where we were at. So we'll continue on there. I think we saw this one at the end. But this graph here, again, is the relationship between the rate constant and the temperature. And if you just think about generic rate law, just in general, the rate is equal to K times A to the X and B to the Y. For the most part, your rate constant right there, if you have a very large rate constant, that is going to essentially increase the rate, right? Because it's all multiplying there, right? So if you had a big number for the rate constant, that would probably result in a larger overall rate. Vice versa, if you had a small value for the rate constant, right, that would give you a smaller overall rate when you multiply it across. So just simple math there. If you just think about logically, that's sort of the relationship between the rate constant and sort of the rate of the reaction. Obviously, as that goes up, then the other one goes up. And that's what we see here at lower temperatures. Again, smaller rate constant, increasing the temperature, a much higher rate constant, and thus a much higher sort of speed. So we talked a little bit about frequency factor, which is what that A is. And a reminder that the R here is the energy version, which is 8.314 joules per Kelvin per mole. But basically, you can think of A as the proportion of molecules that really do possess enough energy to get up and over that activation energy. And as we talked about there, increasing the temperature will increase the average kinetic energy and thus increase the amount of molecules that have enough to get up and over that barrier. And obviously vice versa there. If you lower the temperature, you probably will also lower the rate. And that's what we see in this graph here. This is basically the activation energy where it occurs. And these are two different temperatures. The red line is a higher temperature than the blue line. And what we see is when we look at sort of the blue line, which is the lower temperature, only this much in terms of molecules have enough energy to basically get up and over to the other side. By increasing the temperature, what we see there is not only this much, but now all the way up here, that amount of molecules now possess enough energy to make that activation energy. Again, the result of that is obviously more reactants will go over to product side, and the result is an increase in the rate of that particular reaction. Any questions on that there? Okay. So as we saw it on the previous slide, once again, a couple other important things to keep in mind here. Once again, the temperature here does need to be in Kelvin, so you gotta make sure you do your 273 plus the temperature in Celsius. The other really important thing to watch in this equation and sort of its other version, which we'll talk about here in just a second, are these two guys right here. And the units that you have going on with those two guys. Now, typically speaking, when you do give activation energy, as an answer, it typically is in kilojoules, or as I just wrote on the previous page, are in joules. So once again, you have that difference in units, which is a very common mistake that people make, and they find themselves like off by a factor of 1,000. So you got to be really careful on those units as well. Also, the other important thing is we talked about, I think at the end last time, when we look at those energy diagrams, the activation energy is a positive number, right? It's always increasing, always being put in as the hill that everybody has climbed. So when you calculate the activation energy, it should always yield you a positive number when you do that. By the way, this would be the y-intercept. So from your graph, right, that is where your straight line would cross the y-axis, right? And it equals not the frequency factor, but equals the natural log of the frequency factor. So you do have to take the e on both sides there to get rid of it. So again, this is really sort of the graphical version of this equation. So for example, if we had a problem such as this, and we have a bunch of temperatures and some rate constants that go with this temperatures, and you'll do these graphs in the next experiment type of thing. In this case, what we have to do really is use our equation. Our natural log of K is equal to minus E of A over R, 1 over T, plus the natural log of A. We do have to do a couple of things to convert these things into usable units. First off, the temperature here is already in Kelvin, so that's good. But basically, we got to take this column and take 1 over the temperature. So we got to take that column and convert all those values into 1 over temperature. And this is obviously the rate constant, which means we would have to go through that column on both sides there and convert them all into the natural log of K. So again, those are the two things that we would want to graph in our graph here to help us figure that out. And if we went through that and did that, we would then graph the correct guys on there, and we would get this graph right here, which obviously you could do on something like Excel. And by the way, there are some homework problems where frankly, you got to lay up some graphs or do it on Excel. It's probably the only way to, or the best way to sort of do it. So keep that in mind as you go through the kinetics chapter, you may have to do that. So this is our equation, or y equals mx plus b. And we could use that to answer our question. So in this case, we do want to determine the activation energy and the frequency factor here. So very simply here, the slope is equal to minus E of A over R. So very simply here, our slope is this number right there. So that would mean that we have negative 1.12 times 10 to the 4 is equal to E of A over 8.314 joules per Kelvin per mole. We're basically going to multiply the 8.314 to the other side, not just the 8.314, but here's the importance in terms of the sign, right? We got to take the negative to the other side. That's going to give us our positive value that we're looking for. And that means that we would end up with, in this case, using our exponent button, 1.12 times 10 to the 4 times 8.314-ish gets us 9311680. The units here are actually, again, in joules because of the gas constant in this case. We can divide it by 1,000 there and end up with, I feel like, which I want to time 1.12 to the fourth times 8.314. There we go. I think I missed a decimal point there. Sorry, 93116.8. There you go. Now we'll divide it by 1,000. Going to give us 93.1 kilojoules as our activation energy. Any question on that there? Again, positive number typically given in kilojoules is typically how you should report that. Any questions on that one there? Now we could also find the frequency factor, which is A in that equation. And if you remember, if we go back a page here, that is y is equal to mx plus b. So b is equal to the natural log of A. So b in this case would equal the natural log of A. And our y-intercept in this case is 26.8. So that would give us 26.8 is equal to the natural log of A. To get rid of the natural log, once again, we're going to E both sides there. And when you do that, the natural log goes away and we end up with we'll call it 4.36 times 10 to the 11, it looks like. Now the question is, what are these units? Well, we took the natural log of A, right? And that is the y-intercept. So the units of the y-intercept, or what is graphed on the y-intercept, is the natural log of K. And since we took the E of that, basically, we got rid of the natural log, which means for the most part, when you calculate the frequency factor, basically it will end up with the same units as K. So we would want to use the same units here as K, which would be 1 over molar seconds would be our typical units here for this particular one. And that's because basically the y is the natural log of K. To solve for it, you're taking the E, which gets rid of the natural log, which means we get back to the same units as K, basically mathematically speaking. Any questions on that? So this obviously would be a more graphical approach to figure out activation energy and the frequency factor. You do need to know how to do this. My guess is I would not have you graph it, but maybe the graph would be laid up to you and you need to know how to get the information off of it. Yeah, any questions on that there? All right. Who wants to make graphs all the time? Nobody does. So technically speaking, this is what's sometimes referred to as the 2-point version of the Arrhenius equation. Basically 2 points from the line, the straight line there, and you could calculate everything that you need. And this is probably in most cases the version of the equation that you would use the most. So these are our normal sort of characters here, if you will. These are the rate constant at 2 different temperatures. These are obviously the temperatures that do need to be in Kelvin, right? This is again our R that we were just using, which is our 8.314. And that obviously is our activation energy, right? Once again, I would say in this equation here, those units of E and A and R is really where people again run into trouble. There's a few different versions of this equation. So if you look in other places, you may see 1 or 2 other versions of this equation where they kind of distribute the negative to the outside and they combine the denominator. Sometimes you'll see it written, but they're all basically the same equation here. So you could take 2 points. If you know 2 rate constants, you can figure out maybe the temperature. If you know 2 rate constants and the 2 temperatures, you can figure out the activation energy. So you can really solve for any of those 3 things. A rate constant and an activation energy are a temperature. Oddly, people always want to do the math wrong here. So just so we're clear, you want to divide first, yes, and then take the natural log. So not the natural log of both of them and then divide. So you want to divide that first and then take the natural log of it. Any questions on that there? All right, so why don't we try one here? Reaction there has a rate constant of 2.57 at 701 Kelvin and 567 at 895 Kelvin. What is the activation energy? So all right, let's take a look here, see how we're doing. So we're going to use our 2-point version here. So we got a little natural log of K2 over K1 equals a little E of A over R, 1 over our temperature minus 1 over our temperature. In this particular case, we're actually good in terms of temperature. It is in Kelvin. Once again, if it was in Celsius, you do need to do that conversion. Everything else we got, we could actually plug in. So here our natural log of our K2, which would be our 567 divided by our 2.57. It's equal our E of A, which is what we're looking for, 8.314 joules per Kelvin per mole. 1 over our initial temperature there is 701 Kelvin minus 1 over our 895 Kelvin in this case. Doesn't matter which one you choose as 1 and 2. The answer is it doesn't. So most people just take the first one listed as 1s, second one listed as 2s. The important part is as long as you keep the rate constant and temperature together that go together, whichever one you call 1, you keep them both together, it'll come out the same. In this case, I'm going to kind of clean up the left-hand side there. So we'll do 567 divided by 2.57. Then I'm going to take the natural log of it. That's going to give me a 5.396453. We'll take it a few digits. E of A over 8.314. Going to also clean up what's in the parentheses there on the right-hand side. So 1 divided by 701 minus 1 divided by 895 gets me 0.0003092, I think. Mathematically, I should do what first? I need to multiply the 8.314 to the other side. Then I need to divide by that. Yes. So multiply first, then divide. So doing that move right there, multiplying the 8.314 times 5.9, nope, 5.3, 96453, dividing by 0.0003092. It's going to give me an E of A of about 145,104. These units, once again, will be joules based off of the gas constant. Put it into kilojoules, about $1.45 kilojoules happening there would be correct. Question on that there. Obviously divided by 1,000 or it's a kilojoules, yes. Any questions on it? Yes, sir. Technically, yeah. So sometimes the units don't perfectly cancel out on a lot of the stuff here we do, but it would be these. It would be kilojoules basically per mole would work. Yeah. Other questions? Okay, so let's try another one here. See what we do. Let's try this one. It's often said, as we talked about earlier, that if you increase the rate or the temperature by 10 degrees Celsius, you will double the rate. So calculate the activation energy in this case. Here's a couple of hints and temperatures you could use if you like. See what you come up with. Okay, let's take a look. So really in this case, we're doubling the rate. So, there's a variety of ways you could think about this, but basically this value here needs to end up as a 2, basically, right? And basically you could do just like what they did here if you like and put those values in, but ultimately it does need to equal 2 because it was doubled. So you can even use real numbers if you want, 4 over 2, whatever you want to do, we'll get you to 2. But that's essentially what we're going to be putting in there. So the natural log of our K2, which would be 2 times K1 divided by K1. Again, those guys cancel, giving us the natural log of 2, basically is what we need in there. Will equal our E of A over our R, which is 8.314 joules Kelvin mole. And once again, in this case, they really just took sort of a 10-degree difference in the temperature. You can take anything around room temperature, you'll get approximately the same value. You won't get exactly the same number if you obviously chose maybe a couple of different temperatures, but it'll be kind of ballparkish. So in this case, they went with 300 Kelvin, if I'm not mistaken. And our second temperature there was 310. Once again, we're going to kind of do the same math here. We're going to take our natural log of 2 really on the left, which will give us our 0.693 equals our E of A over 8.314. Once again, I'm going to clean up what's in the middle there on the right. 1 divided by 300 minus 1 divided by 310. Going to give us 0.0001075. Once again, we're going to do the same math. We're going to multiply to the other side, then come back and divide by what's there. That will give us 0.693 times 8.314 divided by our 0.0001075. Going to give us a activation energy. Once again, that's going to end up here in joules as 53596 joules, or about 53.6 kilojoules in this particular case. Once again, we got a positive activation energy, which we should end up with in this case. Any questions on that? Yeah. It is. So technically, most people honestly will kind of display the activation errors as just kilojoules. If you want to leave it kilojoules per mole per Kelvin, it's actually still there as well. Actually, the Kelvin will kind of get away here, but so it really would be kilojoules per mole, which is perfectly fine if you want to do that, or if you want to leave it in kilojoules for me. There'll be times as we go through these calculations, their units really won't cancel out perfectly and stuff like that. So typically joules or kilojoules for energy, and usually activation energy is in kilojoules. So if you leave it like that, but technically speaking, when we natural log here, all the units kind of go away here. The K's cancel here. So technically speaking, it is still joules per mole when you get to the other side. So kilojoules per mole is really what's left over. So if you want to leave it just kilojoules, it's okay. Yeah. Because I really wasn't paying attention to quick, but in this case, we really didn't have a lot of numbers at all to work with, to be honest with you. We kind of made up our own numbers in this case. So really the only number we have would be 1 sig fig, which you might not want to take it to in this case. So I just went with 3. Yeah. Other questions? Yeah. Are you always, I'm sorry? You should wait to round to the end. Yeah. So in most cases, I take what's on the calculator, continue on with the calculation, and then kind of clean it up at the end. Yeah. In this particular case, there was pretty much not very many numbers at all given to us. That we weren't even really given temperature other than what they gave us. So you can kind of think of it almost as, you know, you can't give any sig figs in this case would be sufficient. I probably wouldn't go extreme and go to 1 like the temperature value, because you know it's kind of tight. Other questions? Questions on the Arrhenius equation, the relationship between temperature and the rate constant. Again, the relationship obviously, as we talked about, increasing temperature increases energy, increases the proportion of molecules that have enough to get to the other side. The result of that is we do see an increase in the rate, and we usually will see it as the increase in the rate constant to sort of show us that, and vice versa. Obviously, if we cool everything down, opposite is true. Any questions on any of that stuff there? All right. So the last thing we're going to talk about in terms of kinetics is reaction mechanisms. And as we sort of talked about this the other day as well, remember that not all collisions do result in products being formed. There's really kind of a couple of things that should really happen in order for a reaction to take place or products to actually form. Is there does need to be a collision. So really these two guys need to hit each other. Collision theory is sometimes called. And they do need to hit each other in the right location with the right amount of energy, as we talked about last time, in order to allow really the bonds to start breaking, new bonds start forming, all that good stuff. And as you can see in the top case, we do get products formed. In the second case, although these guys will collide with each other, this is basically the wrong sort of location for products to occur. So again, it's an important thing to remember that just because two things sort of come in contact with each other, it doesn't necessarily mean that you will make products. So it's not always perfect. You're gonna, every hit gets you a product. You got to hit the right spot. You got to have the right energy for that to basically occur. How reactions occur or take place is an idea of what is referred to as the reaction mechanism. Now, the idea of reaction mechanism is pretty much this. It's the idea that not all reactions basically take place in like a one-step move. So for example, if we were looking at a reaction like A plus B goes to E plus F, this reaction does not necessarily take place in just one move to get yourself to the product side. It may happen in several individual steps or individual reactions. So maybe like A plus B react to make C plus D, then like C plus D react to make E plus F. And maybe it happens in sort of a two-step process. If we were to add these equations together, by the way, when we add equations together, anything that's on opposite sides of the arrow will cancel or reduce. You can kind of think of the arrow like an equal sign. Anything that's on the left-hand side stays on the left-hand side. Everybody on the right stays on the right. So in this case, the C's on the left, the C's on the right, they will cancel. This will cancel. This will leave us the overall reaction of A plus B. If I know how to write letters, there we go. A plus B gives me E plus F. So this is sort of the idea of everybody's favorite thing, right? Which is like Hess's law, where you take all those individual reactions, you add them together to get an overall reaction, and you keep track of all the energy and the stuff that you do to those individual reactions to take place. So it's kind of the same idea. The idea here in reaction mechanisms is based on sort of the kinetics of it. We want to sometimes propose a possible mechanism or pathway by which this reaction could actually take place. Doesn't mean that this reaction takes place through this pathway every single time. It doesn't. It just means it's a plausible sort of path for this reaction to happen. So all these individual steps are what are sometimes referred to as elementary steps. So we take a bunch of small little sort of reactions and we add them together to get us our overall reaction that we're looking at for. And that gives us our reaction mechanism as a way this reaction could take place. Now, when we look at this reaction here, which is NO plus some O2, makes some NO2. During this process of this reaction, N2O2 is actually detected. But as we can see from the overall reaction, it is nowhere to be found. So that obviously means a couple of things. It means that obviously somewhere along the process here, we have to make some N2O2, which is why it's going to be detected. And secondly, along the process here, that N2O2 needs to disappear by the time the reaction is done. So clearly this cannot be a one-step move where we go from reactions to products, because you have to account for that guy being made and going away. So a plausible sort of mechanism for this reaction to take place is what we see on the bottom there. Perhaps in the first step of the mechanism, we actually make a couple of N2O2s, or make an N2O2. Then in the second step of the mechanism, it is then used to make the product. When we would add these together, once again, this guy and this guy would cancel out. This is what is, we will see in the next page, referred to as an intermediate. An intermediate is some type of substance that gets made early on in a mechanism, but it gets used up by the time the reaction is over. So this is a possible way that we could account for what is seen when this reaction takes place, that perhaps we make this N2O2 to begin with, and then it gets used up in the next step. Any questions on that there? Now, an intermediate is, as I just mentioned, something that gets made early on in the mechanism, but the really important part of it to know whether or not something is an intermediate is it should never show up in the overall reaction. So it has to be made early on, it has to get completely used up, and it should not appear in the overall reaction. So there will be times where perhaps you cancel out some things when you add up some equations, but you do not completely cancel them out. And those things still remain in the overall reaction. So even though you cancel them out, they are not an intermediate because they're still there in the overall reaction. So again, for it to be an intermediate, it's got to completely go away by the time that mechanism or reaction is complete. Any questions on that there? Yeah. It is not. So that's a really important distinction for something to be an intermediate. It's got to pretty much be made early on in a mechanism, and then it's got to be completely used up by the time the reaction is over. And that's what we see here when we look at the N2O2. We make it early on, then we completely use it up. It is not seen here. So it's not seen in the overall reaction. And that's what makes it an intermediate for sure. Now, if we were to reduce down the N2O2 and we still had one left over and it found its way to the overall reaction, that would not be an intermediate in that case because it's part of the overall reaction. So that's a really important part of what makes something intermediate. It's got to go away. It's got to be made and then go away. Just sort of a transition sort of guy that gets you to your products. Yeah. And maybe one, it may be more than one as well. So there may be more than one intermediate along the way in the mechanism. And again, that's sort of how you could look for it, whatever completely cancels out. Other questions? Now, when we talk about these elementary steps, which are really the basis of these mechanisms, we could classify them as one or a few different ways. One is a unimolecular step or reaction. Unimolecular means it's just one molecule that's reacting. We could have a bimolecular, which means there's two molecules reacting. Termolecular would be three molecules reacting. Each of these steps up here on top would be what type? It would be bimolecular, right? Two guys there, two guys there. So both of those elementary steps would be bimolecular in this case. They both have basically two guys reacting. Any questions on that there? All right, so how do we know if what we are dealing with is a sort of good mechanism or bad mechanism? And that ultimately is a lot of times sort of the question you're asked in these type of problems is this a possibly good mechanism? Or is this like perhaps not such a great mechanism for a particular reaction to take place? To help us understand and figure that out, there's a couple important things that we need to sort of talk about when we look at a mechanism. The first thing is, if you remember in kinetics, as we've talked about the entire chapter here, when we go to write a rate law and we figure out a rate law, the orders for each of the reactants are found experimentally, and we do not use the coefficients from the equation. The one and only place where you can actually use the coefficients from an equation to write a rate law is right here when you are doing mechanisms, trying to prove whether or not this mechanism is a good one or a bad one. So for every elementary step that you have, every elementary reaction that you have, you could actually write a rate law for it just based on the coefficients that you see in the equation. So for example, here, if I had A goes to products, I could write a rate law for this step, which would be the rate is equal to K. Basically, coefficient here is 1. We could use it as a 1 here, basically. The second one here, A plus B, could give us a rate law of K times A to the B. And this right here is basically 2A, right? Going to products. So that is where the 2 comes from. So this is the one and only place in kinetics where you could use the coefficient as the orders and everything will be okay. Again, normally if it's not a mechanism problem, you should not do that. You should do it the way we've done before, you know, rate 2 over rate 1 and all that kind of stuff. But here it's okay. So when you look at a mechanism, what are really the two important things to look at and to help you determine whether or not this mechanism is a good one or a bad one? The first one is pretty simple. When you take all the elementary steps, so all the individual steps of the mechanism, and you add them together, and you cancel out everything that cancels out, what you are left with should be the exact equation or reaction that you're looking for. So if you add up all the steps to the mechanism and you get the reaction that you're looking for, then it's good so far. Obviously, if you add up all the steps and you don't get that reaction, you get a different equation or something, it's a bad mechanism. So that's a very simple, straightforward one. You got to add up all the parts. All the parts give you the reaction you're looking for. It's good so far. The second thing that you have to look at or think about is this. There is going to be a step in the mechanism which is considered the rate determining step. The rate determining step is sometimes abbreviated as RDS, or the rate determining step. It is the slowest step in the mechanism, hence the turtle, I think. So it is the slowest step in the mechanism. It is the one that basically determines how fast or slow that reaction is going to take place. Again, it's kind of like the 10 items or less, and the guy's got like, 400 items in front of you. You're not going to get through that line until that person gets through there. They're like your rate determining step. So it's kind of the same thing here. There will definitely be a step along the way that is the rate determining step. How do you figure it out? Well, first off, the rate determining step, if you write the rate law for the rate determining step, it should be the exact same rate law as the one that's found experimentally. So in typically these type of problems, a lot of times they will give you the experimental rate law was found to be this, or the observed rate law was found to be this. If you have one of the steps in the mechanism where you go and then write the rate law by using the coefficients for the orders, and it matches perfectly to the one that was found experimentally, then that would mean that that is the rate determining step. That is the slow step in the mechanism. All the other steps should occur a lot faster than that, and that's the one that's really determining your overall rate. The other way in a mechanism problem, as we will see, where you figure out which one is the rate determining step, it is frankly really hard to do because it is the one labeled slow. So that would be the rate determining step. So in mechanisms, you'll have some steps that are labeled fast, and you'll have one that's labeled slow. That is the rate determining step. So that's the other way. Very commonly, we can figure that out. So those are really the two things you want to make sure of. All the steps add up to the overall reaction. Does the rate determining step have the exact same rate law as the one that was found experimentally? And that oftentimes could help you. Any questions on that there? All right. So let's take a look at this here. Why don't you try a couple of things here? Why don't you figure out these three things? Here is a possible mechanism for a reaction to take place. The rate law is found experimentally to be K is equal, the rate's equal to K times NO2 squared. First off, what is the overall reaction? What are the intermediates? And what can you say about the rate of the first step versus the second step? Here, C. So let's start with the first one. It should be the simplest thing. I want the overall reaction. So these are two elementary steps. So simply, I just need to add both of them together here. Anything that's on opposite sides of the arrow could cancel or reduce. So that could go away. That could go down. That leaves me, everything on the left will stay on the left. So that leaves me an NO2 plus a CO. On the right-hand side of the arrow, everybody stays the same. NO plus CO2. Any questions on that there? What is the intermediates here? NO3. Anything else? Is NO2 an intermediate? It is not an intermediate, although we did reduce it down. NO2 is found here in the overall reaction, which means it is not an intermediate, right? So the only intermediate here actually is the NO3. Any questions on that there? All right, so what do we want to know about the rates of the first one versus the second one here? Since this is a reaction mechanism, we could go back to each of these elementary steps and we could actually write a rate law for each of them. So if we were to write the rate law for the very first elementary step here, we would use the coefficients there to help us do that. And in this case, it would be, for the first step there, the rate equals K times NO2, and it would be squared, as that is one NO2 there, and one more makes two NO2. The rate law for the second step here would be the rate is equal to K times NO3 times CO. Again, we could just use the elementary steps and write a rate law here when we're doing mechanisms. First off, any question on how we got both of those there? So why would writing the rate laws for each of these steps be helpful? Do we see anything that matches perhaps? Do any of the steps match the experimentally found rate law? They do. Which step? The first step, right? First step here has a rate law of this that matches the rate law that we see was found experimentally. When a step in a mechanism has the same rate law as the one found experimentally, that means that step is which step? That would be the slow step, or the rate determining step, right? Would be step number one. So step number one should be slow, right? Versus step number two, which should be faster than it, right? So in this particular type of mechanism problem, because we were able to match a step to the rate law that was found experimentally, we know for sure that the first step in this mechanism is actually the rate determining step, is going to be the one that's really the slowest in all of the mechanism, the one that basically will take the most time and really determine the overall rate of that reaction that's occurring. Any questions on any of those answers? Yes. Will the rate law always be given? I'm going to say in most cases. There are certain mechanism problems, and we might have the very last example, might be an example of it may not be given to you. But in most cases, it will be given to you in one form or the other. Yep. Other questions? Yes, sir. Because in order for something to be considered the slow step in the mechanism, or really what's known as the rate determining step, the RDS, it should have the exact same rate law as the one that's found experimentally. And that's because really it is the one that is the overall reason the reaction is going either fast or slow. So they have matching rate laws because it's really the one that determines the overall rate of that reaction that's occurring. So in this case, step one had an identical rate law to the one found experimentally. So that's how we knew it was the slow step. Other questions? All right, so this is one type of reaction mechanism problem. There are a few different types of problems. So let's take a look at another type of mechanism problem. And we'll go through this one here together to kind of show you kind of the steps that you might want to take in a problem like this. So first off, the idea here is this type of mechanism problem is one where there would probably be more words that's up there, but it would probably ask you something like, is this mechanism a plausibly good mechanism for this reaction to take place? So basically what they're asking you is it good or bad, basically? So is this mechanism a good or bad mechanism for this reaction to take place? So once again here, we want to answer really the two questions. The first question is, does adding up all the steps here give us the overall reaction we're looking for? And we could also think about the rate determining step in that. So this is the overall reaction here that was given to us. So that would be a really good thing to do here, is simply take the three steps in this case and we're going to add them together. So we're going to add all 3 steps here together. So we're going to do a little bit of crossing out, perhaps. Looks like that will cross out. Looks like that might be it, maybe. Nope, that will cross out. And that might be it at that point. So at this point, everything on the left-hand side is going to stay on the left-hand side. So if I go to the left-hand side of all those arrows, I have 2NO plus 2H2, which is this guy and this guy right here. Going to the right-hand side of the arrow, I got 2 waters and an N2. So by adding up all these reactions together, the first thing to check off our list is they do match, right? So we got all the reaction that we're looking for, so that is good. So you can kind of think of these problems like in math, like the proof problems, like you have the answer, but you got to prove, is it good or bad, right? So it's kind of that idea. The second thing that we have to make sure of is the rate determining step should have the same rate law as the one that's found experimentally. So that is with the rate law on the bottom there. To the right is the observed rate law. So in this particular mechanism, which step is the rate determining step? It is the second one, and we know that because it says slow, and it's as simple as that, yeah? So in this case, we do know that the rate determining step should be this guy because it is the slow step. So if we take the slow step and write the rate law, we would have that the rate is equal to K times H2 times N2O2, right? Now, there's a couple of important things that we should talk about, I guess, before we got there. But in this particular case, what is the intermediate in this reaction? Or A intermediate in this reaction? Which ones were the intermediates in this case? N2O2, right? It completely canceled out. And also N2O, right? Those are actually both intermediates in this case. Neither one is found in the overall reaction. So when I go look at my rate law that I have for my rate determining step, and I go and say, does it match this guy? Do they match? The answer is you can't make that determination at this point. They clearly do not match because they don't have the same things in there. In order for them to match, or in order for you to compare, you have to do like the old saying, compare kind of apples to apples. Yes, oranges, oranges. Because the rate law for the slow step here has an intermediate in it, we have to get rid of the intermediate using a little bit of math so that we can then compare rate law to rate law of things that are not intermediates. So the goal here is I need to get rid of the intermediate that I find in my rate law here. So to do that, I want to go back to my mechanism, and what step has that in it besides the second step? It's only the first step, right? So the first step is the only one that has this guy in there as well. So we're going to use the first step and a little bit of math to get rid of the intermediate. Now, when we look at the first step, there's arrows heading in both directions. Yes, that is what we like to call a reversible reaction in chemistry. That means just as fast as it goes the first way, it will come back the other way, and it will reach what is referred to as chemical equilibrium, the major topic of this class, which we will talk about in the next chapter. So we could actually write 2 different rate laws for the first step. We could write a rate law going from the forward direction, which is this way. And we could write a rate law going in the reverse direction. So if we wrote the rate law going in the forward direction, it would be the rate is equal to K1 times NO squared. And that would be going in this direction. Yeah? We then could write a rate law going in the opposite direction, which means that the N2O2, our products, would actually be our reactants going in the opposite way. The second rate law that we could write is that the rate is equal to K to the minus 1 times, N2O2 in this case. And that is going in this direction. Any question on how I got both of those things? So from that one step where it's a reversible reaction, we could actually write two rate laws for them. And because eventually what will happen is they will reach equilibrium, which means the rate of the forward direction will equal the rate of the reverse direction. This rate right here and this rate right here, should they be the same or different numbers? They will be the same number because the forward direction and the reverse direction will be going back and forth at the same rate. Who cares what that number is? I just know that it should be the same number. And because those two are the same number, what can I do with the other part of each of those things? I could set them equal to each other. So K1 times NO squared would equal K to the minus 1 times N2O2. Any questions on that there? What is my ultimate goal again? I want to get rid of the N2O2, right? So that means I'm going to divide this to the other side. And I will get that K1 times NO squared divided by K to the minus 1 will equal N2O2. Yeah. Now, do I have something that I could substitute in there for N2O2? I do. So at this point, what I could do is I could take what I just solved for, this entire thing, and put it into here. And if I do that, I will end up now with a rate law for my slow step of the rate is equal to K times H2, substituting in what I got on the bottom there, K1 NO squared divided by K to the minus 1. All the little K's, they are the rate constants, yes? Rate constant a different number or the same number? Once again, the rate constant, is it the same number or different numbers? Same number. So again, although I don't know what the K's are in this case, I do know K on top, K on the bottom are going to cancel, right? Which will leave me now a rate law that is the rate is equal to K times H2 times NO squared for my rate law for the slow step that has everybody in there that's not an intermediate. Now, when I go and do my comparisons of my rate law that I solved for and the rate law that was found experimentally, are they the same or different? They are the same in this case, yeah? And we're able to confidently say that because we got rid of the intermediate. So because this is the same rate law for the slow step, the rate determining step, as the one found experimentally, and because the overall reaction, when you add up all the steps, gives you the overall reaction, this is a good mechanism. A happy-dappy mechanism right there. It's a good mechanism, is what most people would call a plausible mechanism. Again, doesn't mean it will always occur this way, but this is a good explanation for the way it will occur. Any questions on any of those steps? Yeah. Yeah. Yeah, we basically substituted out the N2O2, which is the intermediate, for what we solved for using step number 1. So we needed a way using the mechanism to basically get rid of the intermediate and leave us with something that's not an intermediate. And we were able to do that by basically math and substituting out the relationship of what N2O2 is equal to based on the first step and putting it in there. Yeah. Other questions? Yeah. Say it again. We were able to do a substitution, and what'd you say? Yeah. So if your question is, didn't mean to cut you off, but if your question is because it didn't match the first time, but it matches now, is it a good mechanism? The true answer is we weren't really truly able to compare the first rate law to the one found experimentally because the first rate law had that intermediate in there. So even though it didn't appear like a match, it actually did in the end once we were able to get rid of the intermediate. So the answer is you really are not allowed to sort of compare a rate law that has an intermediate to one found experimentally because you're not really knowing what you're looking at until you kind of do the substitution out and stuff like that. So again, it's not sort of a apple to apple comparison, and it will probably always never match in that case. And you really won't know really does it match or does it not match until you kind of do the math and substitute out. Other questions? It's fun times, good times had by all. All right. Well, I did one. Why don't you do one? Is this a good or bad mechanism here? By the way, this 2 actually is over here. I got kind of lost up there. All right, take a couple minutes, see if this is good or bad mechanism.